All right, today we're going to look at the urinary system a little differently. I want you to forget everything you know about basic plumbing. Instead, let's think of it as one of the most incredible, self-regulating computers you've ever seen. A biological processing plant that keeps your entire body online and running smoothly.
So let's just start with this idea. What if your body actually ran on software? You know, with lines of code, complex feedback loops, and powerful processing units all working together. Well, the thing is, in a lot of ways it does, and the urinary system is probably one of the best examples of this biological code in action.
So first things first, let's talk about the system's core mission. Every piece of great software has one primary goal, a main objective, right? And this biological system is no different. Its entire reason for being is to keep the body's internal environment absolutely perfect.
And that prime directive has a name: homeostasis. Now don't let the fancy term fool you. This is the ultimate goal of the software. It's all about maintaining a perfect internal balance of water, salts, and pH, no matter what you're doing or what's happening outside. It's what keeps the whole network from crashing.
Okay, so to keep everything that stable, the system has to be constantly cleaning things up. And that's where excretion comes in. You can think of it as the main waste export protocol. It's not just about, getting rid of stuff. It's about actively identifying and removing corrupted data, like toxic materials and other junk, to keep the system running clean and efficient.
So we get the mission, but what's actually executing all these commands? What's the hardware? Well, the mainframe of this whole operation, this central computer, is the kidneys and all their connected parts.
And this picture lays it out perfectly. You've got your two kidneys right there. Those are the main processing units. The big vessels, the renal artery and vein, are basically high-speed data cables, bringing blood in to be processed and sending the clean blood right back out. And the bladder? Well, that's just our temporary storage drive.
But the real magic, the really mind-blowing stuff, happens when we zoom way, way in. Because inside those two main processors are millions of tiny individual units that do all the heavy lifting.
Just look at that number. Over 1 million. And get this, that's the rough number of microprocessors, what we call nephrons, packed into each kidney. That is a staggering amount of parallel processing power, all dedicated to filtering your blood 24/7.
And here's what one of those million-plus units actually looks like. This is the nephron. Every single one is its own little self-contained cleaning station. Blood flows in, it gets processed through all these complex little tubes, and waste is systematically pulled out.
The whole process kicks off right here, in the glomerulus. The best way to think of this tangled-up ball of capillaries is as a high-pressure security gate or a firewall. It uses pressure to force water and tiny particles out of the blood while making sure the bigger, more important things, like proteins and cells, stay inside. It's the first and maybe the most critical step.
Okay, so we've got the hardware down, but hardware is just a fancy paperweight without software to tell it what to do. So now let's get into the operating system, the hormones and chemical signals that run the whole show.
The most fundamental protocol in this entire system is something called osmosis. This is how the system moves its most valuable resource, water. It's a really powerful passive data transfer protocol that pulls water across membranes to balance out salt levels. This is how the body makes sure it reclaims exactly the amount of water it needs.
And the things controlling these processes are our system regulators. If you imagine the body's master control system, then hormones are basically commands sent through a command line telling the kidneys precisely how to adjust their performance based on what's happening in real time.
And just look at how specific these commands are. Let's say you're getting dehydrated. The brain issues the conserve water command using the hormone ADH. Or maybe your blood pressure is a bit low. No problem. The system runs retain salt and water command using aldosterone. These aren't vague suggestions. They're precise software instructions sent to the kidney hardware.
And the level of precision here is just astounding. This biological code works around the clock to keep your blood pH at almost exactly 7.4. That's not a range, it's a critical, non-negotiable data point. If it drifts too far one way or the other, that's a fatal system error. So the software is constantly making these tiny adjustments to lock that value in place.
But what happens when this incredibly elegant, self-regulating system fails? What happens when the hardware breaks down and the software just can't keep up anymore? Well, that's when the system crashes.
A system crash is basically what happens when a huge number of those million-plus nephrons go offline. When they fail, the system loses its ability to clean the blood. Waste and toxins start building up to dangerous levels, and that triggers a critical failure that puts the entire network at risk.
So what's the fix? Well, this is our external workaround. Hemodialysis is, for all intents and purposes, an external kidney. It's like emergency maintenance. A machine takes over the job of the failed hardware, routing the blood out of the body, cleaning it, and then returning it. It's a total lifesaver, but it's also a pretty clunky solution for a broken internal system.
Which kind of brings us to this final thought. Think about it. The best technology we can build, our computers, our phones, our software, it all needs constant updates, patches, and maintenance just to keep working. So the real question is, how does this unbelievably complex biological code with over 1 million processors and countless feedback loops manage to run, self-repair, and adapt for an entire lifetime? It's really a testament to a level of design elegance we're still just trying to catch up to.